Okay, so this is part 2 of the lab problem video. I just wanted to show you that I made a couple of corrections to the lab procedure. I'm sure several of you caught this, episode 1 through 9 in the last video. It is actually 1 through 8. And also I thought it would be good if I just clarified a couple of things, because it did ask for the velocities, so that means it needs to have a direction. I did draw up here originally that the cart was initially going in the positive direction. I think they mentioned that too, cart A. And that after the collision, my guess was they're going to go in the positive direction, but we don't know the mass of B, so that's not totally true. I mean, we're not sure. So I just basically clarified something right here. Cart's A velocity, VA equals V, cart A velocity. And yeah, I didn't define what these two things meant. Cart A's velocity equals V sub A. So that's done here. And it's directed in the positive direction. The velocity of the cart stuck together after the collision equals V prime. And that's right here. Its direction will be determined by observation and should be included in the table. Alright, so I did that. I also I know it might have been hard for y'all to read some of this. I put how I was calculating the velocity. I didn't have to state that explicitly, but I'd probably want to draw arrows over here in this. Basically, is this the best way to find velocity? No, but it works. I don't want to have to get into like, I would do this with PowerPoint. No, just on this, it's like super easy just to find the velocity. Just dividing displacement over time. So, yeah, just those two clarifications on this, and we'll get into the next part. Okay, so part B wants to know, or part B basically says, there will be sources of error in the measurements taken in the experiment, both before and after the collision. For your experimental procedure, will the uncertainty be calculated in the calculated value of the mass of cart B? Will the uncertainty in the calculated value of mass of cart B be affected more by the error in the measurements taken before the collision or by those taken after the collision, or will it be equally affected by both sets of measurements? Justify your answer. Okay, this is one of those ones to where really anything you put is fine as long as it's not human error and as long as you justify it well. Okay, so this is a reasonable answer. The putty that makes the cart stick together tends to flatten out with use. Additionally, the edges of the sticky note might begin to curl up after multiple trials. Therefore, there is a greater chance for error in the measurements taken after the carts collide. Really, anything you put, but right here, they're basically looking for systematic error. So just as long as you don't mention human error, and you'd want to be careful because you could be like, oh, student 4 and student 3 couldn't coordinate. That's human error. Well, student 4 and student 3 not coordinating, sticking the sticky note at the exact same time, that's not technically human error. That's just like, I don't know. It's got humans. I'd stay away from it. Blame it on the Post-it note. That's just easier. Or you could have said they were the same because the table wasn't level, but I kind of already took care of that. There was a little bit of friction. Really, any systematic error will work. Okay, this one's kind of weird. I don't think their graph is so great, but watch out for this. So a group of students took measurements for one collision. The graph of the students' data is shown. Notice it is a position versus time graph, and they have this little legend, the big dot's cart A and the little dot's cart B. I'm going to kind of highlight these because I did not see them, the little dots to start off with. And if you notice, it's really difficult to see, but see, these have big dots and little dots in them. So that tells me that your collision occurred probably right here. Or not probably, that is where it occurred. So right through here. Oh, no, actually, take that back. The collision occurred at 1 second because that's where the dots start coming together. So that's your collision. This one's really hard to read. Oh, there's the bell. I'm at school. Sorry about that. Okay, so yeah, so your collision occurred at 1 second. And then see, because this one isn't moving. All right, so they want to know, given that mass A is 0.5 kilograms, use the graph to calculate the mass of cart B. Explicitly indicate the principles used in your calculations. All right, principles used in your calculations, that's probably conservation of energy, conservation of momentum, work energy theorem, Newton's second law, all that good stuff. Objects in free fall. I'm guessing because it's a collision, it's probably momentum. First of all, just a quick review of what to do with the graph. Position and time. First of all, does the slope matter? So hopefully you know the slope of position versus time is meters over seconds. So the slope is velocity. Okay, area would be meters times seconds. There is no slope of a position time graph. Now let's take a look at what's going on here. Okay, so what I have done here is we know that the velocity of cart B is just 0. So it's staying at the same point, which they've said is 1.5. I said it was a meter in my setup back here, but the students who did this 1.5, it's up to them. Anyway, so I did that. The slope 0, no velocity. And this is what you should do with cart A. You do a best fit line. So I'm just going to do, I'll start this here and go right to here. That's about right. That's what you would expect to see. Best fit line, it's like the trend line on Google. So this blue line is the velocity of cart A. So let's take a look at that really quickly before the collision. Okay, so this is, okay, so just to be clear on this, the velocity before the collision of B, which I'm just going to call VB, is 0. Okay, and the velocity before the collision of cart A, which is right here, it goes from 0 to 1 and up to 5. So your rise is 1.5 divided by your run, which is 1. So that means that the velocity of A, this is before the collision, is 1.5 meters, that's an M, per second. Okay, so we have that. All right, so now I'm going to do another best fit line for after the collision. So get a line. I'm going to start it here, and I'm going to end it like right up through here. Try and get one that looks, I'm going to put it right here on the 2 to make my life easier. Alright, let me just change the color of that to green, sorry, and make it a little heavier so I can really, really see it. Okay, so let me zoom in. It's my best fit line from there to there. It's not perfect because I kind of made the line heavy, but that's okay. So this is from 1 to 2 seconds. So, and it looks like it went up from 0.5 to 2. Okay, so here is my velocity afterwards. Sorry, it's like a really huge pen I'm using. Okay, and we said that it was from, your rise was 1.5 to 2, so that is 0.5, and then the run, 0.5 meters, and then your run is, okay, so they only did this for a second, but I said to record it for 2 seconds in my thing, that's fine, is 1 second to 2 seconds, so that's over 1 second, so that means V prime is 0.5 meters per second. Okay. Okay, so just to reiterate what I got from the graph, I would write that down. I'm just writing down what I know to figure things out. So I've got mass A is 0.5 kilograms. They state that. I don't know what mass B is. That's what I'm trying to figure out from this information. Let's see. Velocity, this is from the graph. Before the collision, the velocity A is 1.5 meters per second. Velocity B, that's a 0, not a D, because the car's at rest. And then afterwards, oh, I kind of deleted this, but the green line right here, it's positive 0.5 meters per second. So that's after the collision. So I just kind of wrote down what I knew to stay organized. Okay, now is the time to write down some assumptions. Let me make this a little bit bigger. Okay, So after I've written down kind of what I already know to stay organized, I'm going to put assume no outside forces act on system. And I define the system as cart, track, earth system, just in case. I put therefore it's an isolated system. Therefore momentum is conserved. So you always want to get those assumptions in somewhere. If I'd written them earlier and drew a line, that's cool too. Alright, not sure if you can see this, but I did this for me to stay organized. I kind of drew a picture for what momentum before and momentum afterwards are. So just kind of like quickly redrew the mass of cart A, mass of cart B, wrote their velocities. And then did, like, see, I put mass A, that's supposed to be a plus mass B right here, and then I put its velocity in which direction it was going. That's just something I like to do to stay organized. But you don't have to, but it might help. Okay, so I hope you can see this. I just took, since I've drawn my pictures, the momentum before would be the mass of cart A and the mass of cart B, plus, well, we got mass of B and mass of cart A times velocity of cart A. So here I've got mass of cart B and velocity of cart B, but V is at rest. This is all 0. See? V 0. So I'm just going to put the Ghostbusters no smoking sign over this. Just cross that out because it doesn't exist. And then I've got the two stuck together, mass of A plus mass of B equals V prime. Okay, so that leaves us with mass A times velocity A equals mass of A and B added together times velocity prime. And what I'm going to do now is isolate this whole parentheses thing. See, I've got these two added in here. I need to isolate that. So railroad tracks. I'm going to get rid of V prime. What you do to one side, you got to do to the other. So this is just, remember, this is just divide. So I'm going to divide by that. Nothing cancels out because that's a VA, remember? So we've got that right there. Okay, so we still need to get mass B by itself, so I'm just going to subtract mass A from both sides. Okay, so that should give you mass B equals mass A times mass A times velocity VA over velocity prime minus mass A. Remember, you can't take this out of there. It's a fraction thing. Just leave it ugly. Don't simplify. Okay, so I plugged the numbers in, and I did the railroad track thing. So I said the mass of B is mass of A, which is your 0.5 kilograms, times velocity of A, which we got from the graph, is 1.5 meters per second. Remember, meters goes in the numerator, seconds in the denominator. And then we're dividing that essentially by V prime, velocity prime. So I just flipped it. So that would be your 0.5 goes down here in the denominator, and the 0.5 goes with the meters, and then seconds just goes up top because we flipped it around. And then, of course, we're going to subtract the mass of A. So I'm going to cross out seconds, they go away. I'm going to cross out meters, they go away. And what luck, this 0.5 also goes away. So you're left with just kilograms. So you have 1.5 kilograms. So that's its mass, good, minus 0.5 kilograms. That's awesome. That makes things really easy. So yeah, my mass B is 1 kilogram. Super easy.